So, for the first order logic we had seen the semantics, then came to calculations, informal proofs, and then developed the proof by resolution technique. The next in the sequel should be our axiomatic system, and the axiomatic system we will call it as FC, first order calculus, and this will be an extension of the propositional calculus we already had. So, that means the 3 axioms and the inference rule MP will be kept as they are, and we have to add certain more things because of the quantifiers. Again for the quantifiers we will take only one quantifier for each x, because the other one can be introduced with a definition by using the not, De Morgan's rule we have, right. So, like if you have there is x, you can introduce it as a definition with not for each x, not x, fine. Just the way we have introduced the connectives by definitions, the same way we can go for the quantifiers. So, but we have to take care of the special predicate, equality predicate, that might give you some axioms or inference rules, something we have to introduce there. So, these are the extra things we need for FC. So, let us start with FC. So, again our axioms will be axiom schemes. So, we are not using there exists symbol. So, that means we have the alphabet, we will have only these symbols for each, and then not and implies, okay. These two are the connectives and this is only the quantifier, and then we will also use the equality predicates, okay. All the other things like predicates, terms, variables, they are as they are, only restriction will be up to this, okay. This along with predicates, function symbols and so on. Okay. So, we will start with the axiom schemes. The axiom schemes of FC are as follows. So, here we will be using x as a variable, then we have ST for terms and x, y, z for formulas. So, with this we will have the axioms. First one will be our earlier axiom for PC. So, that will be x implies y implies x, okay. Next A2 is the distribution of implication, which is x implies y implies z implies x implies y implies x implies z, just like your PC. Then we have A3, which is for the negation sign. So, not x implies not y implies not x implies y. So, that should give us x, right, law of contradiction. Then we have the other axioms peculiar to FC. So, first we will take the quantifier form for each x x implies x x by t. So, now you are doing something like universal specification, but then this term t there are some restriction on it, fine, that this, what was the restriction, can you recollect with universal specification? Yeah. So, that means x should be free for the term t, x is not only free, x should be free for t. So, write provided x is free for t in x, okay. Next we have another for implication sign itself. So, for each x let us write y, y implies z implies y implies for each x z. Here again this is not a valid formula for every y, but it is valid when x does not occur in y, right. So, let us write it provided x is not free in y. Okay. Then we should have something for the equality. So, let us write say t is always equal to t, okay, reflexivity, and next we will have s equal to t implies if you have x s then we should get x t. Fine. So, substituted is remaining in the formulas, that is what we wanted. I think that should do. Then we will have the inference rules of FC. So, as earlier we will take modus ponens which says x, x implies y, therefore y, and then universal generalization, that is from x you can conclude for each x x, but there is again a problem, always you cannot infer from p x, you cannot say for each x p x, right, it will allow something wrong. So, what should we have is x should not be free in the premises, right. So, in fact, when you come across the proofs, if it is not occurring at all in any premise, that might be a bigger constraint. What we need exactly is till now whatever premise has been used, x is not free there, then there is no problem, right. So, we will just write provided x is not free in any premise used thus far. Right, that much should be sufficient. Then, as earlier, we will be introducing theorems, proofs, right, consequences, and so on. So, first thing is we should define what a proof is, right. So, as earlier, a proof will be a sequence of a finite sequence of formulas, okay, where each of the formulas occurring in that sequence should be either an axiom or it follows from earlier formulas by application of inference rules, right. So, for MP when you apply, you need two such formulas, earlier two formulas. When you apply UG, you will need only one formula, right. So, it should follow from that. So, follow from means whatever is in the denominator, numerator must be there in the proof already, denominator should be, we will be telling that it is derived from that or it follows from that. That is what a proof is. Next, we should define what a theorem is. So, as earlier again, a theorem is the last formula of a proof, fine. We are going so formal, it looks funny, but that is what it is. So, theorem is simply the last formula of a proof. Next, we will be introducing consequences, or rather probability of consequences. So, for consequences we will again take sigma is a set of formulas, and x is a formula. So, we will write sigma entails x in FC now. So, this FC often we will omit once we know that we are working in FC. So, sigma entails x if if there is a derivation of x using formulas from sigma. So, the formulas in sigma are again called the premises. And what is the derivation? Just like your proof, you will be having a derivation. So, again derivation is a finite sequence of formulas, where each formula is either an axiom or it is a premise, it is a formula from sigma, or it is derived from earlier formulas, right. So, similarly this symbol can be used for the theorems, right. So, without anything on the left side, which means now a derivation is a proof without any premise, it allows that, right. Then we will introduce also inconsistency. We will say that sigma is inconsistent if for some formula x we have both sigma entails x and sigma entails not x, right. So, that means we have a derivation for sigma entails x, we have a derivation of sigma entails not x. Otherwise, we will say that sigma is consistent. Fine. So, here really inconsistency is nicely defined, consistency is not, because consistency says that it cannot be derived. Whatever x you choose, either x cannot be derived from sigma, not x also cannot be derived, or one of them can be derived, the other cannot. It is difficult to show, right, but inconsistency maybe you can show it, you can demonstrate it by having two derivations, one for sigma entails x, one for sigma entails not x. Okay. So, we will see some examples how the proofs go there. Okay. Now, this is a familiar theorem. Yes, the first theorem in PCB we proved was this, P implies P. So, you can use the same proof exactly here also, that will prove for each x x implies for each x x, right. But here with quantifier axioms and quantifier rules, we can have a different proof also. So, let us try that how it goes. Okay. Okay. First is, we may say for each x, x implies x, which axiom is it? See, provided x is free for t in x, so I can take t equal to x itself. So, x is free for x in x. Now, then this becomes x itself, there is no change, x is substituted by x. So, it is simply F4. Okay. Next, we will go for each x, x implies x implies for each x x implies for each x x, where from it comes. Just check it, say y is your x, y is you have to take for each x. So, what we need is this is suppose I take for each x, this is x, then I would get for each x here, for each x z here, right. Condition is x is not free in y. So suppose I take y as for each x, then x is not free there, right, but it needs one for each x here, that is the only thing, right. So let us put it. Fine, now it is all right. So this is A5. Okay. Next we want this one, so that we can apply MP, and this can follow from this by UG, because there is no premise used. So it says the restriction on UG is that the variable x should not have been free in any premise used till now. No premise has been used, right. So it can always be used. So third line we may say for each x, x implies x. This comes from 1 by UG. Is that okay? Then fourth is by modus ponens for each x implies for each x. Okay, let us take some more example to see something which is not in PC. This is really coming from PC, this theorem. Okay, it is P implies P, though we have a different proof now instead of using just P implies P form. Fine. So this is your familiar rule of renaming. You have say Px or Py here, for each y Py should entail for each x Px, right. Y has been substituted by x. Fine. Yeah. So what is the condition? X is not free in x, right. We may say a better one, let us say x does not occur in x, then provided x does not occur in x. Suppose this is given, fine, it should be all right. So let us see a derivation. So again we will not be fussy about writing derivation or a proof, we will just write proof. We may write a derivation. Now we can use this as a premise, that is what it says, and then finally we should have for each x, x y by x. So let us write that as a premise first. Now which one we should choose? A4 in which form? For each y x implies x y by x, because that is what we want, right. So x is your term t now, which satisfies the condition required there. The variable y should not be free, should be free for x, right. It is free for x because x does not occur at all. Fine. So this is your A4. Then you have modus ponens, which is x y by x, then UG, that is the natural thing. And UG is applicable. Constant is x should not occur free in for each y x, that is the only premise used, right. It is not free because it does not occur. Okay. you can interchange the quantifiers. Okay. This should be easy to go. All that you need, get x and then go on generalizing, right. So, we start with our premise for each x for each y x. Second, we go for each x for each y x implies for each y x, x is substituted by x, that is all, right. So, this is allowed by A4. Okay. Next, we conclude for each y x by modus ponens. Next again for each y x implies x, A4. Next modus ponens. Now, we slowly generalize. So, 6 for each x x u g, it is allowed because in the premise x is not free, variable x is not free, that is the only premise we have used. Then again for each y for each x x u g. Well, we can start with the premise always for each x not x, that is a premise. Then we can say not x because this is an axiom, yeah, A4. Is that right? Then modus ponens gives not x. Now, from not x we want to infer not for each x x. No axiom says that, right, no inference rule is there, fine, but we can always infer from for each x x x. Can you see some relation between this? See, you have not x, you want to infer from this not for each x not x. No, it is not for each x x, you want to infer this, right. So, look at the other side, can you infer this for, yeah, by A4, this is really A4 and MP, fine. Now, what is the relation between this and this? So, this implies this implies this, contraposition, we can always use PC theorems because it is an extension, right. If you do not want to use the theorem, you have to duplicate its proof, that is all, fine. So, let us use PC theorem, which is contraposition. Now, with contraposition, which one we want? For each x x implies x, this is an axiom. Okay. Next, we say for each x x implies x implies not x implies not for each x x. Okay. This is contraposition, we will just write as theorem, it is already proved in PC, right. We have already proved it as a theorem. If you want to find what is the name, you say contraposition. Fine. Next, by modus ponens we reach not x implies not for each x x. Next, use not x and modus ponens. Okay. So, I am not writing again 6, it is the previous line, so only remote line I am writing as 3. So, 3 6 modus ponens gives not for each x x. Now, let us take one more example. Suppose you take this, which looks very simple, but we do not have any axiom for it, we do not have an inference rule. Okay. Symmetry of the equality relation. So, anyway, we will start with the premise. Next, A7 in which form? Well, again A7, if you look along with MP, see, it will be easier to think about the consequences. That is why you think always with MP instead of the axioms. Suppose A7, A7 I can think of this as a consequence this way. Okay. If I have already S equal to T, I have already x of S, then I can infer x of T. Intuitively that is what A7 says. Okay. Now, by application of MP twice. Okay. Now, we want to find out that T equal to S is inferred. So, our x T should be T equal to S, right. So, x should be equal to S equal to S, right. But if you say, see, there is a problem, writing in this form giving the problem. If you write in the correct axiom form, it should not. Suppose I write this as x x by S, and this is x x by T, right. So, now you can think of x as x equal to S, fine. So, the axiom way we are writing x x by S is not exactly x of S, because you cannot substitute S by T directly, you have to substitute by a variable, and that gives also freedom, you can substitute partially, right. Is that okay? So, we start with our x as or rather axiom 7 in the form S equal to S, S equal to T implies x equal to S implies x equal to T, right. This is the axiom we want. So, this x will become, now this is S, this x will be substituted by T, that is what we want. Is it right? So, this x we are going to substitute by S. So, we start with this form of the axiom. Is it clear? So, to give a comment, to make it readable, you may say A7 x equal to S, that is all, that will make it readable. Right. Okay. So, next we go for modus ponens. Next we introduce S equal to S, this is A6, and again by modus ponens T equal to S. So, this is how we will be doing the proofs and the derivations. Then immediately we should go for the meta theorems which should be helpful for us, right. That is how we saw in PC. Okay, let us formulate monotonicity. So, we start with two sets of formulas, one of them is a subset of the other, and then we have another formula if sigma entails x, then gamma entails x. Also we had another form, if well we go the other way, right, or you can write it as if gamma is consistent then sigma is consistent, fine, but we will be proving this, fine. So, now how do we prove first one? There is nothing to prove really, it is the same proof as PC, right, because there is a derivation, is the definition of the theorem itself, definition of the consequence itself. Similarly, this one also, once sigma is inconsistent, there is sigma entails x, sigma entails not x. So, by first one gamma is inconsistent. Okay. Second one implies first one, that will come only after reduction upside down. First one implies second is easy. Okay. Now, let us go to deduction theorem. So, this will say let sigma be a set of formulas then you need two formulas at least, x y formulas, then sigma union x entails y if and only if sigma entails x implies y. Okay. So, one part of this should be easy, just an application of MP. Suppose sigma entails x implies y, right, then there is a proof of it. So, take that proof, say call it P1, it starts as 1 something and some m which gives x implies y. So, all the premises are used in sigma only, fine. Next you introduce x which is a premise. Okay. So, now you have used premises from sigma union x and then m plus 2 is y by modus ponens, that is all. So, this says sigma union x entails y, just an application of MP. So, that means sigma entails x implies y gives sigma union x entails y, the other part we have to show now, assuming sigma union x entails y, so that sigma entails x implies y. So, if you remember we had done the proof by induction, right, the same method will be used here again, but then why repeat? There is something extra here, right. So, let us see that. Say we proceed with our assumption sigma union x entails y. Our aim is to show that sigma entails x implies y, right. Now, since sigma union x entails y, what could be this y? Things, y is an axiom, second is y belongs to sigma, third is y equal to x. So, it belongs to sigma union x, right, fine. Anything else? Anything else? How can this come? That is what our problem. How can y follow from sigma union x? So, there is a proof of y, that is what it says, right. So, let us take one simpler case, say there is a proof of sigma entails y, x has never been used. First let us take that case, some way it has been derived where x has never been used, right. So, next case we will take x has been used in the proof, right. So, x has been used in the proof. Proof of sigma union x entails y. In this case, how the y follows from sigma union x. So, y can follow because of all these things anyway, we are not using that, it can follow by application of some inference rule, right. So, it can follow by an application of MP or it follows by an application of UG, right. So, and MP has been used. And the last case is x has been used in the proof of sigma union x entails y and UG has been used. These are all the cases y can follow. Fine. In each of these cases we should show that sigma entails x implies y. Fine. Now, let us see first case A, y is an axiom. Then how do you say sigma entails x implies y? We want x implies y, not y. See, our aim is to show that sigma entails x implies y. So, this is our aim, to show that sigma entails x implies y, right. So, you need axiom 1, you need axiom 1 here, right. So, case A, we give a proof of sigma entails x implies y. So, start with y axiom, some axiom, which one we do not know. Next, y implies x implies y, A 1, therefore, x implies y by modus ponens. Okay. So, this is a proof of sigma entails x implies y. Even sigma has not been used, so it does not matter, not that everything has to be used. Next case B, y belongs to sigma, same proof, instead of axiom, if it is B, you will be writing here premise for B, everything else remains as it is, right. For A you proceed like this, for B instead of axiom you write P, it is a premise. Then also it says sigma entails x implies y, clear. Now, let us take case C, y equal to x, x implies x is a theorem, right. Hence, by monotonicity we do not need monotonicity, right, but since we have proved, let us mention. Okay. Next case D, sigma entails y. What to do here? Just like this, case B, just like case B, right. If sigma entails y, then you have another proof of up to this line y, where only premises from sigma is used, then add this to that proof, right. So, add the proof in A to the proof of sigma entails y, right. You have sigma entails y, so already up to this you have the proof, right. Y is the last line of that proof, sigma entails y. Then continue this way, you get sigma entails x implies y. That is all. Next case, now we will need induction. It has been obtained by MP. Suppose it has been obtained by MP. So, we have a proof where y has been obtained, right, and you have sigma union x, where x has been used really, right, that is the case. Now, once y has been obtained by MP, you have another formula z implies y before it, so that MP has been applied, fine. Is that okay? Next use the induction hypothesis on this, right, use the induction hypothesis. You are proving it by induction on the proof of sigma union x entails y, right. So, now this says sigma union x entails z implies y, that is what it shows. Okay. Then by induction hypothesis you have sigma entails x implies z implies y. Is that okay? But then since you have applied MP, you also have z before it somewhere, right. So, apply again on that, you get sigma entails x implies z. Now, add to this proof, add to the proofs of this and proofs of this, right. So, suppose this has been proved by P1, this has been proved by P2, then what you do, take P1, next take P2, this proofs. So, here the last line is x implies z implies y, here the last line is x implies z. Next apply axiom 2 implies x implies z implies x implies y. Apply modus ponens twice, once you get this one, next time you use this, you get this one. So, you get x implies y, that is all. So, this step is by induction on the length of the proofs of sigma entails sigma union x entails y, fine. It is just mimicking the same proof as in propositional calculus. So, now we are in case F, fine. You have a proof of sigma union x entails y where UG has been used. Again the proof will be by induction, right. So, you have a proof where you have obtained y by universal generalization. So, that means y must be in the form for each x some z some x, right, because UG has been used. So, then you have z somewhere here on which you have applied, and this x is not free in x in all the premises, but x has been used, right. So, it is not free in x, all these information are there, okay. X is used somewhere and it is not free in x, fine. Now, what do we do? Apply induction hypothesis. So, then you get sigma entails z with x, right. So, we have sigma entails x implies z. Okay. Now, sigma entails x implies z. So, from this by UG you get x implies z with for each x. Fine. All that we need is x should not be free in the premises, and x is not free in the premises, it is not free in the x, nowhere else, right. So, for each x, x implies z. Then use the axiom for each x, x implies z implies x implies for each x z. Which axiom is it? A6 or A5? A5, and condition is x should not be free in x, that is what it is, fine. Then use modus ponens, you get x implies for each x z, that is all, and x has never been used in this proof, right. Okay. So, that is the end of the proof of deduction theorem. We will slowly go to other meta theorems.